When we do multiplication, it is useful to have a multiplication chart. Now, this multiplication chart works in this way, in that we have, along the horizontal, we have one multiplier, and along the vertical, we have another multiplier. So, for example, if we do 6 times 5, what I'm going to do is I'm going to come across, and I get the answer 30. So my product of 6 times 5 is 30. And the nice thing about this multiplication chart is it actually shows us 30 squares here. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I have 30 elements or 30 squares in this rectangle that also represents the answer of 30 here. Okay, so 6 times 5 equals 30. We can do another multiplication. We can do 9, and we could do multiply that with 13. So 9 times 13 gives us 117. And again, the nice thing is we draw a rectangle around here. Okay, we end up with this area has, and you can count them, there's 117 squares in this rectangle here. Okay, so this is how this multiplication chart works. The other thing about this multiplication chart is, if we take a look along the diagonal here, these are all perfect square numbers. And when we show the perfect squares in here, we can see that 4 times 4 is 16. You can see that 3 times 3 is 9. Again, we have a square, 9 square square. And all these numbers along this diagonal represent perfect squares. So let's look at some of these properties of this multiplication chart. Okay, so we can look at our 3 times 4. So if I go to my 3 times 4 on my multiplication chart, 3 times 4 gives me 12. And I can see that there's 12 squares that make up this area. Remember, our length times width equals area. So 3 times 4 equals 12, and we have 12 squares that make up that area in the top left-hand corner. 5 times 7 is 35, and how many squares fill up that rectangle? So if I do 5 times 7, so 5, 7, 35, and I fill up the top left-hand corner here, there's going to be 35 squares in this space. Okay, so there's 35 squares. So this is the nice thing about this multiplication chart, is that we can also see the areas that are involved in here. So 13 times 14, I'm going to go 13 here, across to 14, which is here. Okay, just going to shrink this a little bit. It's going to give us an area of 182. And again, we can also get this rectangle here, and we know that this rectangle has 182 squares in it. Okay, so we got 182. Okay, and we didn't really count all the squares. We know that length times width is equal to area, so we know that length of 13 times 14 gives us 182 squares. So 6 times 5 is 30, and we know that 5 times 6 is 30. And we can see that when we look at 5 times 6, so there's 5 times 6 here. 5 times 6 is going to give me 30 this way. But if I do 6 times 5 the other way, this is also going to give me an answer of 30. Okay, and the reason why is because when we look at the shapes of these rectangles, they're really the same. They're just one is turned 90 degrees to the other. And so this explains why that multiplication can be switched around. So we can always switch around any rectangle and get the same area. Okay, so we can find lots of these pairs that happen here. In fact, notice that this rectangle and this rectangle are the same. I can do this with 9 times 4 is 36. Okay, and I can do it the other way. I can do 4 times 9. That also equals 36. And so what ends up happening is, across this line, diagonal line, on either side of it, notice that it is symmetrical. Okay, there is a symmetrical piece on the other side of that line, and that's because when we switch around the multiplication from horizontal to vertical, we still end up with the same area because all we're doing is twisting that rectangle around 90 degrees. So what do we notice about the pattern? We know that the pairs, when switched around, give the same area. So there are pairs that are the same across the diagonal. Okay, and what I mean across the diagonal is across this diagonal here. And we know that this side is mirrored onto the other side. So we have two unknown numbers, a and b. A times b equals 32. Although I don't know what a and b is, we know that if I reverse them, I know by the symmetry of length times width equals width times length, we know that by the symmetry they have to equal the same product. So number 7 here, we talked about this already, 4, 9, 16, 25, they are perfect squares. Okay, and these perfect squares fall along this diagonal. So all these numbers along this diagonal represent perfect square numbers. So 225 is really 15 squared. 256 is 16 squared. And these perfect squares, when I draw out the area for these perfect squares, well, they're called perfect squares for a reason, because they make a square shape. Okay, so 7 by 7 gives me this perfect square shape of 49. So why are these called perfect squares? Because they make squares.